A very good morning to all of you. And uh, in this lecture, I'll be talking about the magnetic moment of an electron, and assuming that we have one electron atom, uh, and this electron is revolving around the nucleus. Now, a revolving electron is equivalent to a current loop, and we understand whenever there is the flow of current, the magnetic field is associated with the flow of the current. So electron is a charged particle and it is revolving, so it must develop a magnetic field. And when we say that it must develop a magnetic field, it must come up with both the poles of a magnet. So it will act as a magnet when this electron is in motion. So the target of this video is basically to measure, to calculate the magnetic moment of an electron that's revolving around the nucleus. So we have a target of magnetic moment. And the situation is like this. What we have is we have an electron revolving, and this revolving electron, let's assume that it is revolving with respect to a center, and the radius of this orbit is, say, for example, r, and assuming that this electron is revolving, that means we will have the velocity of the electron. So if I have to write down the angular momentum of this electron that's revolving in this plane of orbit, let's assume that the angular momentum, of this electron is L. This L, if I write down it in vector form, it must be r cross p, where r is the position vector and p is the momentum. And we better understand that this L has to be perpendicular to the plane that contains r and p. So the angular momentum that we have is perpendicular to the plane that contains r and p. So if I boil down this thing and write down the magnitude of angular momentum, and choosing L is rp, where p is the linear momentum, and we know this, the magnitude of the linear momentum is the product of mass and velocity. So what we have is an electron, and electron is looping, and this looping electron is equivalent to a looping current, and this looping current gives birth to the magnetic field. So this looping current can be treated as a magnet itself. So what we have is L is r mv. This is the magnitude of the angular momentum. Now, since we have a magnet, this system is treated as a magnet. This magnet has a moment, what is called as magnetic dipole moment. So if I assume, since the electron is revolving, it's assumed that the electron is revolving around the nucleus, then we can say that the we can say that the magnetic, we can define the magnetic moment. Magnetic moment of this revolving electron, So if I choose a symbol mu L, so L refers here to the magnetic moment due to the orbital motion of an electron around the nucleus. So by definition, we understand what magnetic moment is if we have to measure the magnetic moment of a dipole, of a magnetic dipole. We define it as a product of current and the area. So if I write down this magnetic moment in vector form, this must be current times area. So area is a vector, so the product of current and area leads us to the measurement of the magnetic moment. So I use a subscript of L in this case. So again, writing down the magnitude of mu L. So mu L is going to be equal to current times area. Now what we have a circling electron, and it has a radius of r, and I can treat the motion of this electron, if I assume this motion to be circular, and the current that I have here, current is basically the rate of flow of charge. Now, the charge that I have here, if I take the magnitude of that charge equal to E, and I define this current for one complete loop, when this electron makes a complete loop, the time taken by this electron to complete that loop, I assume that time as time period. And I treat that time as capital T. So this I must be equal to E by T. And we certainly can write down the magnitude of velocity. Okay, we have velocity, the magnitude of velocity, what we also call as the speed, the magnitude of velocity. So how can we write down that magnitude? That magnitude of velocity will be the distance that this electron is traveling in completing a complete loop, and that distance is 2 pi r divided by the time it takes to complete one loop. So this is 2 pi r divided by t. So from here I can calculate the t. So what will be t? T will be 2 pi r divided by v. So this will be the time taken by this electron to complete one revolution and to complete one circle in the given problem. So I can measure the current now. I can substitute the value of t in the equation of current, and then I can substitute this current into the original equation, which will give me the measure of the magnetic moment that is generated by virtue of the orbital motion of this electron. So proceeding from here, what we will come up with is we will have I equal to E by. So what was our T? It is 2 pi r by V. So this is 2 pi r, and this V will go up. So this will be my defining current, and this defining current will lead to what is called as the orbital magnetic moment of this electron. And this orbital magnetic moment of this electron will be, this will be EV by 2 pi r times, okay, times the area. So we have a circle, and this circle has a radius of r, And if we want to calculate the area that this electron traverses in its plane, that area will be simply pi r square. So we will have some cancellations here. This pi will cancel, this r square will cancel, and mu L will come up as EVR divided by 2. Okay, so this is the magnetic moment of revolving electron. This is the orbital magnetic moment of the revolving electron. We can further decorate this mu L as, if I write down E by 2m. So I'm multiplying and dividing by the mass of the electron. So here I will have mvr. And this is something what we have already written down. This is the orbital angular momentum of the electron. So this L is mv and r. So mu L is E by 2m times L. Now we have only taken into consideration the magnitude of the charge in our equation. But we know that we are talking about an electron, and electron has the negative charge. Now, if electron has the negative charge, then I can write down this equation in vector form. So in vector form, I will have mu L equal to minus E by 2m times L. So what is evident here is that this direction of the magnetic moment is opposite to the direction of the angular momentum. So what we have a revolving electron, and it leads to an angular momentum, and this angular momentum is, say, in z direction. So this is angular momentum. The magnetic moment is exactly opposite to this angular momentum. So that opposition can be dictated by the negative sign that has been introduced in this equation. So the direction of the orbital magnetic moment of an electron is always opposite to the direction of orbital angular momentum, which is caused by the motion of the electron moving in a circular orbit. Now, if I again write down this magnitude as mu L is E by 2m times L, and if I write down mu L by L is equal to E by 2m. Now this number, this ratio, the ratio between the charge of an electron and the mass of this electron, this is called as gyromagnetic ratio. Gyromagnetic ratio. And in a sense, if I again write down this mu L, and what is this mu L is E by 2m times L. Because we know that the electron that is revolving around the nucleus, it has two dynamical motions. It has two states of dynamics involved in it. One is the orbital angular momentum and another is the spin angular momentum. Again, I would like to make a caution here. The spin angular momentum is not the classical analog here. What we achieve here, what we talk about spin here is just a number. It's a fraction. It can be either 1 by 2 or it can be minus 1 by 2. So in order to differentiate the orbital magnetic moment of an electron from the spin magnetic moment of an electron, what we do is we introduce a constant, say That constant we treat as GL. So we can write down this mu L is GL times E by 2m times L. Now, this GL, for the orbiting electron, the value of this GL is equal to 1. So, if we have obtained the equation of the magnetic moment of an electron due to its orbital motion, the same assumptions can be exercised to obtain the expression for the spin magnetic moment of an electron. So we will achieve the same result, but what will be different will be mu s is gs times E by 2m times L. So for the spin angular momentum, the value of this Gs is equal to 2. So this is how the magnetic moment due to the orbital motion of the electron is differentiated from the magnetic moment due to the spin of an electron. And this GL and GS, they are introduced in these equations to make the difference of this constant number. Otherwise, fundamentally, the two equations are same. Either it's the orbital magnetic moment of an electron, or it is the spin magnetic moment of the electron. There's a difference of GL and GS that can be attributed. Now, we have already solved the problem of hydrogen atom, and what we have seen is when we solved the three important equations that arise while solving Schrödinger's wave equation in spherical polar coordinates, we obtained the conservation of angular momentum. And that conservation of the angular momentum leads us that this L vector, if we have to measure the magnitude of this L, that is equal to under root of L times L plus 1 h bar. Well, this L, this small l, is orbital angular momentum quantum number. And this h bar that we have here, this h bar is h by 2 pi, and we also call it reduced Planck's constant. Planck's constant. So solving the Schrödinger's equation in spherical polar coordinates on hydrogen atom leads us to the quantization of angular momentum. So the angular momentum of the electron is quantized. So I can use the magnitude of this angular momentum in evaluating my mu L. So what is mu L is E by 2m times, instead of L, I'll be using under root of L into L plus 1 and then h bar. So if this h bar comes here, this mu L will be EH bar by 2m times under root of L times L plus 1. Now this term that is in the brackets, what is that? That is EH bar by 2m. This is called Bohr magneton. This is called Bohr magneton. And what we do is we use the values of these constants, like the charge of an electron, which is 1.6 times 10 to the power of minus 19, and we make use of the Planck's constant 6.63 times 10 to the power of minus 34 joules second, and then we take m as the mass of the electron. So when we use all of these constants, what we obtain is we obtain this mu b. So it becomes the fundamental unit of measuring the magnetic moment of atoms. And this unit, the measure of this unit is nearly 9.27 times 10 to the power minus 24. So magnetic moment is the product of current and area. So for current I have ampere, and for area I have meter square. So I can write down the orbital magnetic moment in terms of this Bohr magneton. So that will be mu b times, has to be mu b times under root of L times L plus 1. And if I have to write down the magnetic moment, the spin magnetic moment of the electron, I can write down mu s is equal to, now here I will have 2, if you rightly remember that, gs. This is 2 mu b under root of L times L plus 1. So this will give us the measure of the magnetic moment due to the orbital motion of the electron, and mu s will give us the measure of the magnetic moment due to the spin motion of the electron. And the important point that we have revealed here is that the direction of the magnetic field, suppose the angular momentum is directed in this direction, the magnetic moment of this electron is always opposite in direction to the orbital angular momentum of the electron.